Alright, and so in order to calculate the energy levels, we need to solve the second order differential equation. And just one quick correction, we're going to define this as k squared. Right? So we're going to put a square there. Alright, but as you know, based on our experience with differential equations, in order to solve them, we need some sort of boundary conditions. Right? And so in order to solve our differential equation, what we're going to do is we're going to think about a sort of model system called a particle in a box. And so this is just going to be a framework for describing our ideal gas. And so with this particle in a box model system, we're going to think about literally a box that looks like this. And, where the x-axis, we're just going to think of one direction, x, which goes from 0 to L. And we're only thinking about one direction because, as I mentioned earlier, with the ideal gas, we're assuming the spatial distributions are independent in each direction. And so if we just solve the differential equation in one direction, that means that equivalently we could do it in the other directions as well. In any case, the x-axis is going to be x, and the y-axis here is actually going to be the potential energy of the particle. Okay, so this is going to go from 0 to infinity. And so the whole idea with a particle in a box is that for our ideal gas, the gas molecules can exist inside the box, actually I guess in one direction, and when they're within the box, their potential energy is going to be equal to 0, right? So that falls in line with the assumption for the ideal gas. But if a particle ends up at a wall, then we say its potential energy is infinity, right? And so that essentially forbids the molecule from existing at the wall. And so the probability that it's at the wall, psi squared, is going to be equal to 0. Okay? And that's true when x is equal to 0 and L. And so based on that premise, we could use those as our boundary conditions. In order to solve equation 1. Okay? Alright, so with that in mind, what we're going to do is we're going to go out and solve this differential equation now. So we integrate equation 1. Based on our experience with second order differential equations, we know that this is a standard sort of solution for a homogeneous second order differential equation. Where now we just have kappa raised to the 1. Okay? Alright, and a and b here, these are constants, which we're going to use our boundary conditions in order to solve for. Okay? So boundary condition 1, psi is equal to 0 at x is equal to 0. And boundary condition 2 is psi is equal to 0 at x is equal to L. Alright? And so when we apply boundary condition 1, we get 0 is equal to a sine of 0 plus b cosine of 0. Sine of 0 is 0. First term goes away. Cosine of 0 is 1. So, from applying the first boundary condition, we get that our b constant is equal to 0. When we apply boundary condition 2, what we get is that the left-hand side is 0, and the right-hand side is going to be a sine of kl. Now, there's two possibilities here for satisfying this sort of statement. The first possibility is that our a constant is equal to 0. But if this is the case, then our function is going to be 0 at all x's, right? And so that would give us the trivial solution. And so that's a sort of uninteresting sort of solution. So instead, we're going to consider the other result. which is that instead of A being 0, instead the sine k of L is equal to 0. Okay? Alright, and so that's only true, sine kl being equal to 0, if kl, which at this point I'm now going to rewrite as a pi squared m epsilon I over h squared to the 1/2 times L. This is only true if the inside of our sine function is a integer of pi, right? Or is a multiple of pi. And so if it's going to be a multiple of pi, it could be 1 pi, 2 pi, 3 pi, 4 pi. Essentially, the right-hand side is going to have this integer sort of value, which I'm going to call the quantum number. And so this ni can be 1, 2, 3, ... Okay? And so in this statement here, we know what the right-hand side is. Based on however we define our system, we know what L is. And everything else we know here, with the exception of the energy level. Right? And that's what we want to solve for in the first place. And so if we rearrange the equation, what we get is that epsilon I is equal to this over some of the pi's cancel. Okay? Alright, and so this result we get here, it's simple looking, but it's actually very profound. Right? Because epsilon I describes the energy of our particles. And on the right-hand side, everything here is a constant. But the quantum number here, it's not a continuous function. It can only take on integer values. Right? And so what this result tells us is that not only is a quantum number a discrete value, but the energy of our particles is also going to adopt discrete values. Okay? And so, not only does it adopt discrete values, but it has this is proportional to the quantum number squared. And so that tells us as the quantum number goes up, the energy level is not going to go up linearly, but it's going to go up in a quadratic sort of way. And so we could see this sort of relationship on this figure here, where what is being illustrated is the quantum number on the left-hand side, and then the corresponding energy level. So when the quantum number is equal to 1, we're at our ground state energy level, and we have an energy we'll define as 1. But when the quantum number is equal to 2, then the energy level is going to be larger by a factor of 4 to 1. When the quantum number is 3, it's larger than the ground state by a factor of 9 to 1. So that spacing increases. And it keeps increasing as we go to these higher quantum numbers. Okay? Furthermore, not only can we take a look at the energy level itself, but we could also take a look at the psi function. And so psi is a sinusoidal function. So when the energy level is 1, we just get one peak in here. When the energy level is 2, we get a peak and a minimum, and so on and so forth. But if we remember that psi squared is actually the spatial probability of the particle within the box, when n is equal to 1, what it tells us is that the probability is not equal across the box, like is what's considered in the classical case, but rather the particle is most likely going to be in the middle of the box. When the quantum number is 2, then the particle is most likely going to be at a quarter or 75% away across the box. And as that particle number increases, then the distribution gets split up more and more.